One of the key first steps in any data analysis is to visualize the data. We can pick up a lot of information intuitively by looking at a picture, since pictures access the size, shape, and position parts of our brain in ways that just looking at numbers and lists doesn't. Visualizing the data helps prevent you from making incorrect assumptions about how the data are distributed. Basically, you should always visualize the data. Pretty much every time I skip this very important step, I end up regretting it later, when I discover something that I wish I had known all along and would have known if I had just visualized the data first. As we'll see with all statistical tools, you have to choose the right tool for the right context. Some ways of visualizing data are simply inappropriate for certain kinds of data. Other times, one tool may provide a better picture or snapshot of the data than another. Here are some things to consider when choosing a data visualization tool. What kind of data do I have? Discrete? Continuous? What level of measurement? Do I need to show the relationship between different variables or categories? What message am I trying to communicate about the data? There's no sense in creating a bunch of graphs for graphs' sake if they don't communicate anything individually, or more importantly, if they don't support the statements you're trying to make. And finally, does the picture obscure or misrepresent any important feature of the data? Let's take a look at 7 types of graphs and how they represent quantitative information. First is a dot chart. This is a number line with a dot for each observation placed above its value on the line. Dot charts are used with data that have an interval or ratio level of measurement. They're good for identifying potential outliers, that is to say, values that are different than the rest. They're also good for identifying clusters of observations. But dot charts are uninformative if the data are evenly spread out, without many repeated observations, or if the number of observations is very large. Dot charts are kind of charming, but you don't tend to see many of them in practice. Of course, that shouldn't stop you from using them if they portray your data or your message particularly well. Next, we have a pie chart. This is a circle divided into sections showing the division of a group into categories. Pie charts make use of variables that have a nominal level of measurement. They're good for showing parts of a whole, particularly when sizes are quite different. But they're uninformative if there are too many categories. In this example, we see the distribution of weather stations in the United States. One disadvantage of pie charts is that people aren't always that good at judging the relative sizes of areas. In this example, which is bigger, West or Midwest? It's a little hard to tell. But instead, we could use a bar graph. A bar graph is a set of vertical or horizontal bars whose lengths represent the quantity of a category. They also use a variable that has a nominal level of measurement, or an ordinal level of measurement. And they're good for comparing the relative sizes of categories. Here we see the distribution of weather stations as a bar graph. The pie chart we looked at a moment ago emphasizes weather stations in each region as a part of the whole, but it wasn't that easy to tell whether the West or the Midwest region had more weather stations. Looking at this bar graph of the same information, we can easily tell that the West region has just a few more weather stations than the Midwest region. But if you were only looking at the bar graph, it wouldn't really be that easy to tell which category had about a third of the stations. The bar graph is good for comparing the relative sizes of categories to one another, but the pie chart is better at showing parts of the whole. There's a special kind of bar chart called a Pareto chart. It's named after the guy who invented it. A Pareto chart is a bar graph with the categories or bars ordered from largest to smallest. Pareto charts are good for quickly determining the largest and smallest categories, but they should not be used for ordinal data, only nominal data. In this example, we see the percentage of 4th grade students who achieved the advanced benchmark in mathematics on the 2009 TIMSS, the Trends in International Mathematics and Science study. See that Singapore and Hong Kong did the best in this category. Sweden, on the other hand, didn't do so well. Here's the United States. We can quickly locate countries which perform better or worse. In fact, in this particular chart, the color of the bars indicates statistical difference from the United States percentage. Another chart that's related to the bar graph is the histogram. This is a bar graph constructed for continuous data by dividing the continuum into equally sized bins. Each bar represents the number of observations in a particular bin. The histogram shows the distribution of subjects. That is, it shows the relative number of subjects at different levels of the variable. Histograms are used with variables with an interval or ratio level of measurement, variables that are continuous. They're good for visualizing large data sets. But histograms can be highly sensitive to the number of bins chosen. Here we see a histogram of the state cigarette tax. Look what happens when we increase the number of bins. If the bin size is too small, then the histogram doesn't really give a good sense of the shape of the distribution. If we want to look at the relationship between two different variables, we can use a scatter plot. This is a set of disconnected points plotted in 2 dimensions, showing the relationship between two variables. Like a dot plot, each point represents one subject. The point's horizontal and vertical position represent the subject's value on each of the two variables. Scatter plots can be used with variables that have an interval or ratio level of measurement, variables that are continuous. Scatter plots are good for grasping the relationship between two variables, and for identifying outliers. In this example, we see the height and weight of University of Georgia women athletes. Notice how the scatter plot shows that taller athletes also tend to have a higher total body weight. Most athletes are between 60 and 72 inches, and between 100 and 160 pounds. But one athlete is particularly tall, 75 inches, and another is on the short side, about 56 inches or so. Another way to visualize the relationship between two variables is with a line graph. This is a set of points that are connected by line segments, showing the relationship between two variables over a given range. A key difference with a scatter plot is that the points are connected in some kind of order, such as by time. Line graphs can be used with variables that have an interval or ratio level of measurement, both for the horizontal and vertical axes. And they're good for showing trends over time. Here, for example, we see the tuition for resident freshmen at the University of Illinois. Look how there's a gradual increase from 1970 to about 2000, followed by a much steeper increase from 2000 to 2010. When we looked at the histogram, I mentioned that a histogram shows a distribution. A distribution is a function that describes the likelihood of all the possible values of a variable. In other words, it shows the relative number of subjects that have any particular value of a variable. In this example, we see a distribution of heights. We can talk about the distribution of a population or the distribution of a sample. Just like with other parameters, we usually can't know the population distribution. But we can use a sample distribution to get an idea of what the population distribution looks like, typically using a histogram. In this example, the height distribution is for the sample. We could draw this smooth curve to illustrate a possible population distribution that would correspond with the sample distribution. A distribution can have any shape. There are even some distribution shapes that are particularly important, so important that we give them names. We'll talk about those distributions in a few weeks. For now, let's start with a few characteristics that can generally describe a distribution shape. First is a symmetric distribution. This is a distribution with a reflection point. The left side is approximately a mirror image of the right side. In this example, we see scores on the second exam of Physics 116A at UC Santa Cruz in spring of 2011. If a distribution isn't symmetric, then we call it a skewed distribution. This is a distribution for which one side is taller or heavier than the other. It results from having more or fewer observations above the center than below the center. A left skew distribution has more observations below the center, that is to say to the left, than above. Here in this example, we see birth years of Korean War veterans. Notice how the tail of the graph extends much farther to the left than it does to the right. A right skew distribution has more observations above the center, or to the right, than below. Here's the distribution of cigarette taxes again. Notice how the tail extends farther to the right than it does to the left. In the distributions we looked at so far, there's only been one maximum point. But if a distribution has two maxima, we call it a bimodal distribution. Here we see heart rates for one runner during 3 famous 100-mile races in Virginia. Notice how in each graph there are 2 humps, or maxima. Bimodal distributions usually indicate that the sample is composed of 2 distinct groups that are behaving differently. In this case, the runner attributed the 2 humps to 2 different paces during the race, a fast average pace at the beginning and a slower average pace toward the